I really feel like I should do class with my hood up. I don't know why I'm cold.
It's chilling here.
The air conditioning works very well. I have to compliment whoever designed that system. They knew what they were doing. Okay, by the official clock, it is now 6 p.m. and time to start. Let me tell you what the outline is for tonight. First of all, our second exam is next class meeting, be Thursday of this week. Hopefully, either everyone has either already made arrangements with me to take it not in the class on Thursday, or you're just planning to come to this physical classroom on Thursday. So I have two people, one from each of the peninsulas in Michigan who have made arrangements to take it other than in the classroom here. So, if you were thinking you were going to do something other than show up to the physical classroom on Thursday, you should let me know right away. I would suggest, like, while class is going on, you could zing me an email and I'll read it. It's so late at this point. If you were planning to make other arrangements, then probably the GRCC testing center is about the only option. But, you know, I'll listen to whatever you have to say. Send me a message. One thing I will say is that last time around, I had some people who, I had at least one person who needed to come a little bit early, and I had at least one person who needed to come a little bit late. And a lot of times this is driven by like work schedules. So as long as, you know, that adjustment period isn't too long, I don't mind. And if you just send me an email and say, hey, I probably won't be able to arrive until about 6:30. Okay, no problem. Just let me know. And I'll stay an extra 30 minutes so you get the full time for the exam. And it really isn't a problem for me to show up here at 5:30 because I'm usually at least an hour early. And it's the reason I come in here and do office work. So with my coat on because it's so darn cold, but no, I'm not really complaining. Okay, so that's the first announcement. Secondly, I did post the first topic that comes after the test, and unfortunately, I really probably need to cover that tonight. And here's the reason: if you look on the schedule I published at the beginning of the class, I said that during exam week we would use Tuesday to review, and then we would have our final exam on Thursday. And I found out over the last few days that I'm actually not supposed to do that. So we will, come exam week, we'll have the exam on Tuesday. And that means I've got a little bit of material that I got to squeeze in a bit earlier than I would have. So the plan for tonight is that I will mention a couple things about the test. Then I'll give you, from then up to about 7 o'clock, I will talk about the next topic that's coming up, which is infinite series, power series. And then I will go back to just reviewing and answering questions about the exam. And if there's a little bit of time left after that, then, you know, I'll tell you some more about series. But I'm gonna, what that means for people attending online is when we get to the question and answer thing, you really need to just be brave and speak up. And, you know, if it's possible to do that in a pause when I'm saying something else, that's great. But I know that sometimes, you know, it's not like we're face to face. So if you just have to interrupt and say, hey, I've got a question, then I'll take it. I might say, just a second, let me finish this and then I'll come back to you. But you have to let me know somehow. And typing it in like to the chat box, I probably just will not see it until class is over. So, and that wouldn't be very helpful. So right now I am going to switch over to the document camera, I think, if I can remember how to do it. That's not what I want. Oh, here's the problem. Well, oh, there it is, way over here. All right. If you're joining us online and you haven't looked at it already, I posted this document in, I think it's the week 10 folder. I just posted that this afternoon. So this is a good choice. This is a good thing to look at if you're trying to remind yourself of what's on the exam, and that might prompt some questions. So, you know, maybe a good idea to download that and have that handy for when we break for questions. So then there is also a document on review of power series, and I'm going to give you an overview of power series right now. And then at 7 o'clock, I'm going to, whether this is done or not, I'm going to come back to talking about the exam. Okay, so what are power series? Well, power series are series of the form, and I am following the notation of Erwin Kreytzig here, and I'm using M where calculus books tend to use an N, and the reason is that there's a whole bunch of equations that we do in applied mathematics where you really want to reserve the N for something else. So he uses M as an index, and I found it actually works pretty well. So I changed my style after I read his book. These things have a variable in them, which makes them a function. If you put a different X in here, then you're going to add up different values. And so you have a function rather than a fixed value. Now, what this notation means is, and notice I didn't plug this in, it's because I want to comment on it. Sort of in general, we say M goes from 0 to infinity, but the series doesn't have to start at x to the 0 power. It could start at x to the 50th and then go on up from there. The key is that it goes on forever. And the first term does not have to start here, but as I've got it written, it would be a0 x to the 0, x to the 0 is 1, plus a1 x to the 1, plus a2 x squared, and it just goes on forever. And the mth term is this, amx to the m. This looks a lot like a polynomial. It's just that it doesn't stop. It goes on forever. As a matter of fact, a polynomial is a power series. It's just that after finitely many terms, all of the coefficients are 0. So that's one way of defining a polynomial, although it probably wouldn't make a lot of sense because you learn polynomials like when you're, I mean, it wouldn't be practical because you learn polynomials I don't know, what is it? 7th grade, 9th grade, somewhere in there, and saying, oh, look, it's just a power series, and probably not too helpful. Okay, now these things either converge or they don't. And what we mean by that is you pick a value for x, plug it in there, and if you add up all infinitely many terms, you get some finite value, or you fail to get a finite value. Now, so that means convergence depends on which x you put in here. For instance, the way this one is written, it has to converge when x is 0, because all of the terms, except possibly the first one, are 0. So this is guaranteed to converge somewhere, but it may be just at one point. It is also possible that you might have a, what we call the center of the series might be different from 0. So let me write one of those. B sub m x minus x0 to the m. So this might be something like x minus 5 to the m. And then you have infinitely many terms. Like that. And so the center could be anything. So we don't want to just say a power series always converges at 0, because it might not if the center is something other than 0. But the power series must converge at its center. As a matter of fact, you could say a lot more about the set on which it converges. If the power series, let's say the power series converges at 1 and the power series converges at 2, then it's guaranteed that it converges at every number between 1 and 2. And that'd be kind of a mouthful to say. So the way the nice way of summarizing it is the set of x on which the power series converges is always an interval. Now, you have to understand the interval in the sense that I mean it here. There is a degenerate case when you have an interval that's just 1 point long. Okay, we'll count that as an interval for this purpose. But typically, for any series that matters for solving differential equations, this is really an ordinary old interval, like from 3 to 5 or something like that. Or it might be the interval that's the whole real line. That's definitely a possibility as well. Let me write down a couple of power series, and make this a little less abstract. Suppose we have from m goes from 0 to infinity, x to the m over 5 to the m, so that when m is 0, you get x to the 0 over 5 to the 0, 1. X is 1, you get x over 5 plus x squared over 5 squared, x cubed over 5 cubed, etc. It just goes on forever. That's a perfectly good power series, and it makes sense to ask the question, well, for what values of x does this converge? And as a matter of fact, we'll answer that in just a minute. Here's another one. M goes from 0 to infinity. How about this? Well, this is a common way of writing it, I think. Minus 1 minus x to the m power over m. So that when m is 0, you get a problem, right? So you probably want to start at 1. And then that would be 1 minus x to the 1 over 1. plus 1 minus x squared over 2 plus 1 minus x cubed over 3, and it goes on and on forever. This is a famous one. M goes from 0 to infinity, x to the m over m factorial. And that means, well, when m is 0, 0 factorial is 1, by the way. You get 1 over 1 factorial is 1. When m is 1, you get x to the 1 over 1 factorial, which is 1. When x is 2, you get x squared over 2 factorial, which is 2 times 1. X cubed over 3 factorial. 3 factorial is 3 times 2 times 1, etc. Just goes on forever. Let me write down one more. Then we'll take a look at some of these in more detail. M goes from 0 to infinity. This one looks impressive at first sight anyway. Minus 1 to the m over 2m factorial x to the 2m power. So this one acts a little differently. Every time you bump m up by 1, it gets doubled in here. So you add 2 to the factorial in the denominator. You also add 2 to the exponent on x. So when m is 0, you get minus 1 to the 0. That's 1 over 0 factorial, just plain old 1. Then when m is 1, it goes negative, right? Because you have minus 1 to the 1 power over 2 times 1. 2 factorial is 2. Minus 1 over 2 x squared. Now when m is 3, at minus 1 cubed, that's negative. Over 3, that'd be, no, x is 2 here, right? M is 2. 2 times 2, 4 factorial. And 2 times 2, x to the 4. And at this point, you start to see the pattern. Plus, minus, how come I got a minus here? When m is 2, I get a plus. So plus, minus, then plus, etc. So the next one is negative. The powers on x are 0, 2, 4. The next one's going to be 6. These numerators, as I've written them, are all 1. And then 0 factorial is 1. 2 factorial is 2. 4 factorial, this is 6 factorial. And it goes on like that. So you get x to the 2m over 2m factorial, and it alternates in sign. This one actually adds up to something nice. This is the cosine of x. This one adds up to something nice. This is e to the x. And there's a smattering of these. E to the x, cosine of x, sine of x, 1 over 1 minus x, that we use very frequently, and you should know them. So I should probably tell you them. We got the cosine of here. The sine is this, minus 1 to the m over 2m plus 1 factorial, x to the 2m plus 1. So it looks just like the cosine, except where I have 2m in the cosine, I have 2m plus 1 in the sine. You might notice, by the way, the sine is an odd function. And its power series has only odd powers of x. The cosine is an even function, and its power series has only even powers of x. E to the x is neither even nor odd, and it has both even and odd powers of x in its power series. And 1 over 1 minus x, You actually learned this in calculus, though you probably saw it in a slightly different form. This is simply the sum on x to the m. M goes from 0 to infinity. This is a geometric series. You might have learned the sum as a over 1 minus r. That's probably the form I've seen it most commonly in calculus books. And if you want it to look like that, then the series is a r to the m. M goes from 0 to infinity. And then the sum is simply the first term. When m is 0, you get a. Notice when m is 0, here you get 1, a, over 1 minus r, where r, in the calculus books, they say is the common ratio. This version here, it's worth noting that it's equivalent to this one on the left. Just because if you already have that one memorized, then it's nice to be able to make the connection. But this form over here on the left is much more useful in this course than the one on the right. So we almost always use this. Okay, now it turns out that we can ask questions about power series of the standard questions that you ask about series of constants in calculus, like does it converge or not? Only now you're asking the question for what values of x or t or whatever the variable is, for what values of the variable does this series converge? And we almost always answer that question by using the ratio test. Now, the ratio test in the version that you learn in calculus, I'm going to say this starts at 0, but it doesn't make any difference where it starts. This series converges and actually we say that it converges absolutely. In other words, the absolute values of its terms, that series converges. It converges absolutely if the limit as m tends to infinity of am plus 1 over am is less than 1. That's the calculus version. And just for example, if I have this, m goes from 0 to infinity, how about this? 1/2 to the m power. Well, if I want to test it for convergence, I'd say, well, look at the m plus first term, 1/2 to the m plus 1, divide it by the mth term, 1/2, take the absolute value, which in this case is unnecessary, everything's positive, and then compute the limit. Well, let's simplify this a little bit. Whoops, I got an m up here. So 1/2 to the m plus 1 over 1/2 to the m is just 1/2. And remarkably enough, as m goes to infinity, 1/2 goes to 1/2. And that's less than 1, so it converges. Okay, so that's the ratio test. Ratio test, let me see here. I think we'll do more interesting examples in terms of power series. So anyway, that assures us that this converges. Now, what would it look like if you had a power series? Well, how about this one? M goes from 0 to infinity, 1/2 to the m times x to the m. And we want to decide for what values of x does this converge. Well, what you do is the same thing basically that you do with a series of fixed terms. We're going to compute the limit as m tends to infinity of, okay, you take the m plus first term of this, 1/2 to the m plus 1, x to the m plus 1, divided by the mth term. And now there is a possibility that x could be negative, right? So we do need to actually put in the absolute values here. But of course, this simplifies a lot. Okay, same deal as before. You have 1/2 to the m plus 1 over 1/2 to the m. You're just left with 1/2. And you needn't write absolute values around that. It's already positive. X to the m plus 1 over x to the m. Well, that's x, but remember, it's in the absolute values. And now, what you can't say, well, is that less than 1 or more than 1? Well, it depends on what x is, right? So what you do is you simply set it to be less than 1. You insist that it be less than 1, and then you solve the corresponding inequality. Well, what's the limit over here? Well, the limit is just 1/2, right? So we've got this inequality, 1/2, absolute value of x is less than 1, multiply each side by 2, absolute x is less than 2. So it converges. That's about the worst sigma I've drawn in a while. Let's try again. M goes from 0 to infinity, 1/2 to the m, x to the m, converges if absolute x is less than 2. Now, it will turn out that if absolute x is greater than 2, this will definitely diverge. And the ratio test, however, is inconclusive if the limit turns out to be equal to 1. So the ratio test does not tell you whether this converges at the 2 endpoints. By the way, this is an interval. Absolute x less than 2 is equivalent to this. Minus 2 is less than x is less than plus 2. Now, it turns out if you work through this carefully, you can prove that it converges at, let me see, it converges at neither one of these endpoints. So that is the interval of convergence right there. And notice, we got what we were supposed to do. It's supposed to be an interval, right? You're not supposed to get like the interval from 2 to 3, and then, oh, by the way, if it's equal to pi, it also converges. No, you can't get an isolated point. You always have to get an interval. The interval might be the whole real line. The interval might be the degenerate case of a single point, or it may be an ordinary interval like this one. Okay, let's take this one. I think I wrote this one down earlier. Only I said we better start at 1 because it can't divide by 0. Let's take that one and figure out where it converges. So what you do is you take the limit as m tends to infinity of, okay, you replace m by m plus 1 in this expression, 1 minus x to the m plus 1 divided by m plus 1. And then you divide it by, and I think because I don't want to write fractions that are like 6 lines long, I'm just going to write out the division, then later I can invert and multiply. Divide it by the one where you have 1 minus x to the m over m. And we would take the limit, and I forgot, I need absolute values. So, and then we're going to set that to be less than 1 and figure out what that tells us about x. Okay, actually, this is not real hard. It looks like a lot, but after you simplify, it isn't. Let's take a look at this denominator and this denominator. When I divide, I'm just simply going to flip this fraction over and multiply, right? So I'll have m over m plus 1. And then I'll have 1 minus x to the m plus 1 over 1 minus x to the m. Well, that simplifies to 1 minus x to the 1. However, I have absolute values to keep into view here. And now I'm ready to take the limit. Well, as m goes to infinity, m over m plus 1 is just 1. So this simplifies to absolute 1 minus x, and we force that to be less than 1. Well, okay. That tells us that minus 1 is less than 1 minus x, which is less than plus 1. How about if we multiply this thing through by a minus 1? That would sure help. I'll have 1 is greater than x minus 1 is greater than minus 1. When you multiply by a negative, you have to reverse the sense of the inequalities. And I would like to simply flip this around because I'm not used to looking at it in that order. Minus 1 is the smallest thing, then x minus 1, then plus 1. And then I add 1 to each one of these segments. So I get 0 is less than x is less than 2. So that interval is the interval from 0 to 2. And you could actually decide in this case whether it converges at 0 and whether it converges at 2. But it turns out that in differential equations, it doesn't matter. All the stuff that we will do with these series is only justified on the interior of the interval of convergence. So even, well, by looking, I can tell you, it fails to converge at 0, and it does converge at 2. But just because this series converges at 2 doesn't mean that it does us any good there. It doesn't. The theorems that we need tell us you can do all the manipulations that we want to do for differential equations on the interior of the interval of convergence. So like we want to occasionally take derivatives term by term. It's perfectly legal on the interior of the interval of convergence. So you can do that for any x up to 2, but not including 2. So, and of course, down to 0, but not including 0. So in that open interval, take derivatives all you want, do regular algebra, like add a couple of series together, subtract them, or multiply term by 5 or something like that. That's all fine, as long as you're on the interior of the interval of convergence. At the endpoints, doesn't matter if the original series converges or not, you just are not, you cannot do those operations anyway. So frankly, we don't care if it converges at the endpoints. Doesn't do us any good, even if we. Okay, well, that is, that's a little bit on convergence of series. Let me show you some practical methods for obtaining series. Practical ways to get more series. And the reason I say more is that there are a few series you simply should know. So here are the ones that are absolutely essential. 1 over 1 minus x is the sum. M goes from 0 to infinity, x to the m. And this converges if absolute x is less than 1. So it turns out that, for instance, we could take the derivative of both sides of this and get a new series. Or we could replace x by 5x and get a new series. We could take an antiderivative as well. It's okay. You can do that stuff and get as many series as you need. Another base series that we work with all the time, e to the x is equal to the sum. M goes from 0 to infinity, x to the m over m factorial. The sine series and the cosine series. And I said them before, but I'll write them again so that they're all in one place. Sine of x is -1 to the m. Now sine is an odd function, and that's how you remember that we need odd powers of x divided by odd factorials, the corresponding odd factorials. Sine of x, cosine of x, well, cosine is an even function, so it shouldn't be too much of a shock if we only have even powers of x. And you might notice these sine and cosine series are kind of similar to this, right? Here you have the power of x is matched by the factorial. That's true for both the sine and the cosine, and it's also true for e to the x. Sine and the cosine alternate in sign, and e to the x does not. But it almost looks like there should be some connection between these three functions. And in fact, there is. We've already encountered it. E to the I theta is cosine theta plus I sine theta. And you can actually prove that if you believe these three formulas, then you can see why that's true. So why don't we give it a try? How about if I do a couple warm-ups here first, though? What if I wanted e to the 2x? What I would do is I would take this e to the x series, sum m goes from 0 to infinity. I'll just write empty parentheses here for a minute. Something to the m over m factorial. And I'd say, well, how I get from this series, e to the x equals the sum on x to the m over m factorial, to this one is I replaced x by 2x. So I'll replace this x by 2x. And, I guess that's an okay way to write it. You could write it in a little bit different way, though. 2x to the m is 2 to the m times x to the m. And now it's in kind of that standard form where you have something times x to the m power. And you could ask a question like this. Well, where does this series converge? Well, we haven't done that one yet. So that means we would have to actually probably compute the limit. So let's take the limit as m tends to infinity of the m plus first term, 2 to the m plus 1 over m plus 1 factorial, x to the m plus 1 over 2 to the m over m factorial, x to the m, and take the absolute value, and having done that, compute the limit. Simplicity itself. Eh? Okay, well, this is going to simplify a lot. We're going to take the reciprocal of the fraction in the denominator, multiply it by the numerator. So we'll have 2 to the m plus 1 over 2 to the m. That's 2. In the numerator. In the denominator, I've got m plus 1 factorial. In the numerator, I've got m factorial. Now, remember, m plus 1 factorial looks like this. It's m plus 1 times m minus 1 times all the way down to like 3, 2, 1. And that's going to be on the bottom. On the top is m factorial. Well, m factorial is this, m minus 1, all the way down to 3, 2, 1. And you can see that all of these factors are going to cancel with all of those, and you're going to be left with 1 over m plus 1. And then I've got x to the m plus 1 over x to the m, that's x, but I have absolute values. The only thing that could possibly be negative here is the x, so we'll just put the absolute values there. And now we force this, we say this has got to be less than 1. What conditions on x will make this true? Well, no conditions on x. If you take 2 and divide it by increasingly large denominators, this fraction right here has limit 0, right? So this piece right here, that much is 0. That's 0 times absolute value of x is less than 1. That's 0 is less than 1, and that is always true. So we have convergence. So this series converges for all x. And if you want to write it as an interval, you can. It's the interval from minus infinity to plus infinity. And the claim earlier is preserved. The set of x's on which a series converges is always an interval. This is an interval, all x's. And way back where we were talking about this guy right here, right? E to the 2x is the sum on 2x to the m over m factorial. Okay. Let's take a look at this now. E to the I theta. Well, some m goes from 0 to infinity, and maybe, let me just flip back to the formula. It's whatever you put in the exponent, it's that to the m over m factorial. Now, please be patient with me if what I write seems pedantic, but I've learned from experience that writing out several terms here actually helps. Probably helps most people see what's going on. Okay, when m is 0, I have I theta to the 0 power over 0 factorial. By the way, 0 factorial is 1. Then I theta to the 1 over 1 factorial. And it is going to be probably convenient if I write out about 8 terms. And they look pretty boring on this line. But the deal is it's going to split into two series. So when I split it into 2, I've only got 4 terms apiece. And you need a few to see the pattern. So next, I'm going to have I theta squared over 2 factorial plus I theta cubed over 3 factorial. And this is going to go on. I think I'm not going to quite write them all because I'd like to get done tonight. Let's do the last 2. The 7th power and the 8th power terms. Okay, equals. Now, I am going to split this 0, 2, then there's a 4, then there's a 6, then there's an 8. There are some even powered terms and there are odd powered terms, 1, 3, 5, 7, etc. And They both, of course, go on forever, but I'm just going to rearrange them. And, you know, a reasonable question would be, is that even legal? And the answer is, if you're within the interval of convergence in its interior, yes, it's legal. You can do that. Let's see. I'm going to put the evens first, I guess. I theta to the 0 over 0 factorial. Then I'm going to skip this for now and go to this one, plus I theta squared over 2 factorial, plus 0 to 4th power I theta to the 4 over 4 factorial, I theta to the 6 over 6 factorial, plus I theta to the 8 over 8 factorial. And this goes on forever. It doesn't stop. Plus, now the odd power terms, I theta to the 1 over 1 factorial, plus I theta cubed over 3 factorial, plus I theta to the 1, 3, 5 over 5 factorial, plus I theta to the 7 over 7 factorial. And this one goes on forever as well. Okay, now let's simplify this one. I theta to the 0, well, that's just a 1. And of course, 0 factorial is also 1, but I'm gonna leave it this way. 0 factorial plus this one, I've already made an error here. It's going to be negative. I squared is minus 1. So it is theta squared over 2 factorial, but it's negative because it got I squared. And by the way, I think I want to modify this one. Instead of writing theta 1, which is correct, I'm going to write theta to the 0 so you can see the pattern. Plus, now let's take the 4th power. I to the 4th. I squared is minus 1. Another I squared is minus 1. So it's minus 1 times minus 1, that's plus 1. Theta to the 4th over 4 factorial. And okay, plus, minus, you would guess probably a minus next. Theta to the 6 over 6 factorial plus theta to the 8 over 8 factorial and minus, plus, et cetera, forever. And if you guess that, you'd be right. Okay, what about this one? Well, I've got I times theta. So I've got theta to the 1, and I'm just going to write that over 1 factorial. And I'm just keeping in mind for right now, I've got an I on this term. We're going to deal with it later. How about I cubed? Well, that's I squared, which is minus 1 times I. So that's minus I theta cubed over 3 factorial. And I'm just reminding myself that has an I on it because I cubed is minus I. How about I to the 5th? Well, I to the 5th is I to the 4th times I. I to the 4th is 1. So it's 1 times I, so it's plus I theta to the 4th over 4 factorial. And let's see, 1, 3, whoops, I don't want the 4th power. What am I doing here? Theta to the 5th over 5 factorial. It's that guy. The reasoning is still correct. I to the 5th is I times I to the 4th. It's 1 times I. So there's an I on that, but otherwise it's plus. And how about the 7th term? Well, that would be all the way out here. You have I to the 7th. That's I to the 4th, 1 times I cubed minus I. So minus I times theta to the 7th over 7 factorial. And you see the pattern, plus, minus, plus, minus, plus, minus, only this one, every single term had an I. Okay, well, take a look at this. Theta to the 2m over 2m factorial alternating in sign, that's cosine theta. And this is I times theta to the 2m plus 1 over 2m plus 1 factorial alternating in sign, that's sine theta. Sure enough, e to the I theta is cosine theta plus I sine theta. It works. You can also easily show in this way that the derivative of e to the x is itself. But I'm hesitant to pause too long on that point because there are other things I should mention. If only I could remember what they are. Oh, yes. I wanted to show you some tricks for generating series. That's where all this started. Okay, so let's start with this guy. All right, now there are the standard tricks of doing substitutions. So substitute like 3x for x, then I'd get this, 1 over 1 minus 3x equals the sum, m goes from 0 to infinity, 3x to the m. And normally we split these off so we have a coefficient times the power of x. So that's just straightforward. This one is also straightforward, but it's going to be darn handy. So let's do it. What if I wanted 1 over 1 plus x? Well, I get from here 1 over 1 minus x to 1 over 1 plus x by a substitution. I replace x by minus x. When I do that in the series, instead of having x to the m, I have minus x to the m, which is minus 1 to the m times x to the m. Now, why would I want that? Well, think about this. If I integrate this, I get the log of 1 plus x, right? And what would this thing look like if I integrated it? Well, this is where you start to see the power of these series expansions. Now, every integration and every differentiation is just like you're doing it to a polynomial. There aren't any easier functions other than constants. So how do you integrate x to the m? Well, it's x to the m plus 1 over m plus 1. Now this one, notice, this starts with a power of x that's x to the 1. It doesn't have the constant. So that is a piece all by itself. So then you ask yourself the question, well, what is the constant term? We don't know what that is. The integration doesn't give it to us. If I set x to be 0 here, the log of 1 is 0. If I set x to be 0 here, this whole series collapses to 0. So by setting x equal to 0, I'm doing like an initial value problem. Set x equal to 0, I get 0 on the left-hand side, I get 0 on the right-hand side. So just for completeness, you don't need to write this down every time. But I computed the constant term, and I found out that it's 0. It's that plus C thing you do when you integrate, right? So now I take something this simple. Honestly, I don't know about you. I learned this in high school. So I take something this simple and in a couple of steps, one substitution, one integration, now I've got a series expansion for a logarithm. Well, that's a lot more sophisticated. But the series is really not very hard to work with. How about if we started with this, 1 over 1 plus x, and we took its derivative? Well, that's just x plus 1 to the minus 1 power, right? So its derivative is minus 1, x plus 1 to the minus 2, and the chain rule factor is 1. And so when you clean that all up, it's pretty simple. Minus 1 over 1 plus x, if you want it to sort of look like the other one, minus 1 over 1 plus x squared. Okay, so minus 1 over 1 plus x all squared is, now I start with this series right here, and I simply take the derivative on the x part. It's m times x to the m minus 1. And I had a minus 1 to the m, which I shouldn't throw away. But we should do a little cleanup here. M equals blank to infinity. I'm going to explain that in just a minute. Okay, notice when I put in m equals 0 here, it's 0 times some other stuff. So that very first term contributes nothing. I might as well start this at 1. And I'm going to put my minus 1 to the m back in the front, just because that's the traditional place to put it. And this time I remembered to do it in time. Okay, now you can do another thing here, which, well, I call it index shifting. What if I knocked these m's down by 1? So this now starts at 0. Of course, knocking infinity down by 1 is not going to make any difference. So I'm going to knock these down by 1, but to make up for it, I'm going to push these all up by 1. Oh, yeah, sorry. So now I have this in its standard form. It's a coefficient on x to the m. Now that is, the form I have here is minus 1 over 1 plus x squared. Of course, who would want it this way? You probably want the plus 1 if you're trying to like make a table of common functions and their series expansions. So you just multiply this whole equation through by 1, minus 1 rather. 1 over 1 plus x squared equals the sum. M goes from 0 to infinity. And now you could call this m plus 2, but it works just as well to call it m. And what did I do? I just multiplied by a negative. Those are equal because this can be factored. It's minus 1 to the m times minus 1 squared. Minus 1 squared is 1. So that and that. Okay, so there's some derivations of series. If you work with a few known series, and the most common ones to start with are 1 over 1 minus x. That's the geometric series. Then the series for sine, cosine, and e to the x. And you can generate a whole bunch of other series based on those by applying various tricks. Many textbooks will mention that you can multiply series term by term, and they are correct about that. If you take something like the series for 1 over 1 minus x and multiply it by the sine series, you can do it. But if you think about it, with polynomials, you have those middle terms you got to keep track of. Well, now there's like infinitely many middle terms, right? You got to think of all of the ways of constructing a constant term, all of the ways of making a first degree term, all of the ways of a second degree term, et cetera. I have found that while that claim is true, typically for solving problems, it is so complicated that it's not worth the trouble. And I might better find another way of getting the series I need. So I'll give it a little lip service, but I'll also say that I think it's generally useless. So it's true. You can multiply series. Now, there is one kind of multiplication that is common and is very useful. For instance, sine of x, standard series, minus 1 to the m over 2m plus 1 factorial, x to the 2m plus 1. That's the standard series for sine of x. So what is the series for x sine of x? Well, you simply take this series and multiply every single term by x. So the coefficients are unaffected. Minus 1 over 2m plus 1 factorial, and then it's x to the 2m plus 2. And this is one that I've actually seen pop out using series methods. I've actually seen this function come out as a solution to an equation. Sine of x over x, what's that? Well, it's just this series for the, oops, I forgot an m here, right there on the minus 1. Minus 1 to the m over 2m plus 1 factorial. Now, if I wanted the sine of x, I'd have x to the 2m plus 1. But if I divide that, x to the 2m plus 1 by x, I get x to the 2m. So these sorts of multiplications and divisions by a single power of x, oh, they're very easy and very convenient and often useful. Okay, I think that's enough to get you started on that stuff. And you won't be looking at it until well, sometime after Thursday, probably. So let's leave it at that. All right, I said at 6 o'clock or 7 o'clock, and it's about there now. I would cycle back around to this. So my suggestion is take a look at the list. Does the list spark any questions? And they can be fairly vague. Hey, there was this one thing we did, and
when we sign a second order differential equation in the system of first order equations, and then we find the eigenvectors. In the case of the complex conjugate head, how does that show on the phase plan?
okay.
Like if there's something like a spiral, how do those vectors, like for the moment there were a couple of problems where I found the eigenvectors, but they were complex numbers. And I didn't know what those would mean on a phase.
Okay, okay. So the question is, if you're solving a system of linear equations, and you get a complex eigenvector, so we could make one up. Say you're multiplying then by that, you know, what do you do with that thing, right?
Yeah, mostly when it's a line, so like for the normal points where there's only lines and they either point to a point or they move away from them, the vector is normally something fairly easy.
Yes.
I don't know what that looks like when it generates a spiral.
Well, in a case like this, remember the whole eigenvalue is going to be a real plus or minus an imaginary part. So if, let's suppose it looked like this. Now, this I would expect to generate a spiral. First of all, this is declining in size, and so it's going to be stable. And well, this is two perfectly good complex solutions, Z1 and 2, but how on earth do you get a couple of real solutions out of there? Well, what you can do is the same thing that we did way back with constant coefficient, second order homogeneous equations. You ask yourself, well, how could I get one real solution out of this? Well, I could take the part of this that's real, and then I could also take the part of this that's imaginary. So the real part of Z, and by the way, when you do this, it always turns out that it's good enough to take one of the Z's. The other Z is going to be the complex conjugate of the first one. And if you take real and imaginary parts of both of those, you end up just repeating yourself on the second one. So you just pick one of the two and you take the real and imaginary parts. So the real part of this is going to be 2 times the cosine of 2t in the first entry of the vector. And then let's see, this times this is minus sine of t. So this times this has real part 2 cos 2t minus sine t. And on the bottom, the real part is going to be this times this, 3 cosine 2t. And that's times e to the minus 3t. So there's the real part. And the imaginary part is going to be, let's see, I times that. So I'm going to have cosine 2t. And this times this is minus, did I do that right? Nope, I don't want this. Because this times this is going to be real. So that one's out. And this times this is imaginary. What am I missing? Oh, this one. This times this, 2i. And then in the second component, in order to get an imaginary, you have to take 3 times the I sine t. So 3 sine of t. And again, you have a coefficient of e to the minus 3t. So here are 2 vector solutions that are linearly independent, and they're both real, and that'll do. And you'll get at least something like a spiral, I think. You always see some kind of symmetry when you do this, by the way. You got 2 and minus 1 for the coefficients on cosine and sine. Here we have 1 and plus 2. So it's kind of like that pattern you'd expect with complex conjugates. And this also is true. The complex conjugate of 3 cosine 2t is, whoops, oh, I got a sign there. Well, 3 and 3, but it does switch from cosine to sine. So that second thing I just said, scratch that, it was totally wrong. So anyway, maybe I should make this explicit. So this is y1, and this is y2, two linearly independent solutions. This is one of the good reasons to do that method of complex exponentials for solving second order linear equations with constant coefficients when you have just a sine or a cosine on the right hand side, because you use the same trick once you get to the systems. Okay, any others?
In 2.5, some of the questions you gave us, it was something like with the differential operator, like d squared minus 3d minus 4, and then apply that to something else. But the other thing was also like a polynomial, and I wasn't really sure what we were supposed to do there.
I'm not quite sure what you have in mind. What comes to mind for me right at first, the question is a reference to the differential operator notation. This thing means, well, the cap D means take a derivative. So take two derivatives on y, then take minus 3 times one derivative on y, and this has no derivative at all. So 4y. Now, I suppose then you could have something like this, d squared minus 3d plus 4 times, I don't know what you might see, y plus 2 or something like that. Was that?
I had like x squared plus 3x minus 2.
X squared minus 3x minus 2. Was x a function then?
I think so.
Oh,
It was- I was just really confused by the whole wording of the question.
Sure. Okay, I see it now. All right. Yes, you can do this. I was interpreting the x in the wrong way. Okay. This means you do these things to this function, right? So this means you do these things to this function of x. So you take two derivatives on this function. First derivative would be 2x minus 3. Second derivative would be 2. Then you take minus 3 times the first derivative of this function, which is 2x minus 3. And then you take 4 times the original function. And I might be able to squeeze it in there, x squared minus 3x minus 2. And then, of course, this can all be simplified doing high school algebra.
Okay, that makes.
Which I botch up 50% of the time, so I'll quit here.
I think I was just confused by the wording on it.
Yeah, it's certainly not something that you're used to seeing before you get to this class. And honestly, it's not my favorite notation either. But I think, well, this is a differential operator. There's a whole field of mathematics called operator theory. So I know there are people that just do this all the time. And this would be the shallow end of the pool of what they look at. But I never studied operator theory other than little bits and pieces that pop up here and there, like this. So I don't know what they do.
How well versed should we be in the free spring oscillation section? I felt like there was a lot of manipulations to end up with like the really nice little formulas at the end.
Okay, to repeat the question, what do we really need to know about the mass spring systems? Because, you know, if you work through that, it's pages of calculus and algebra. So here are some basic things you should know for sure. Y represents the displacement from equilibrium. Equilibrium position, we have the idea of a mass being suspended by a spring. So there is a static equilibrium position, and Y is displacement from that position. By the way, that is normally set up in what looks strange at first sight, is the plus direction stretches the spring. So that would be downward normally, right? And the minus direction shrinks the spring, and that would be upward. But anyway, it doesn't really come up. I don't think you have to actually know that to do any of the kind of analysis that we did. Now, there are some forces acting on the mass. The first one is the spring force. You probably should know that that is equal to minus K times Y. The K, by the way, we're going to set all these things up. So there's going to be an M, a C, and a K, constants. All the constants we say, we declare those to be positive. So we can tell which direction things are going. So this is minus K. The minus is there because it's in the opposite direction of the displacement. Displacement is Y. So if you pull the mass down, the spring will try to pull the mass back up. If you push the mass up, and you have the kind of a spring that, you know, works by compression, it will try to push it back down. So it's in the opposite direction of displacement. The spring force, you have the damping force. That likewise has got a negative on it, minus CY prime. The minus is there because it's in the opposite direction of velocity. And then you have the net force. Any mass that's subject to a force will move according to mass times acceleration, which is my double prime, and there's no minus on that. So the net force, my double prime, is equal to, there's only two other kinds of force, the spring, the damping force minus CY prime, and the spring force minus KY. And if you put everything on the left-hand side, you get my double prime plus CY prime plus KY equals 0. And that's the first thing you should know. You should know what these three terms mean. They mean what I've got right here, and you should be able to assemble them in an equation. Now, this is a second-order linear, constant coefficient, homogeneous linear equation. I said linear twice. And what you know is that the solutions of this quadratic are going to control the kind of solution that you get here. And there are three cases. You could have two distinct real roots, a repeated real root, or a complex conjugate pair. Two distinct real lambdas. That means you have two separate y, two separate real values of lambda, and this corresponds to the case of overdamping. By the way, you can see that if you simply apply the quadratic formula here. Lambda equals negative b, that's going to be minus c, plus or minus the square root of b squared, which in this case is c squared, minus 4, a is m, c is k, over 2m. And that's kind of messy in there, right there. That's c squared. Okay, so if you have two real roots, that would come when the stuff under here is positive. And you get that by taking a large C. The C is the damping constant. So big damping, two distinct real roots, large damping is what we mean by over damping, and it's a linear combination of exponential functions. But notice this, you could write it this way, it's two fractions, minus C over 2m plus or minus root c squared minus 4mk over 2m. This stuff in here is c squared minus something positive. So this thing in here is smaller than c. So minus c plus or minus whatever the square root is negative. So in the case of two distinct real lambdas, both lambda 1 and lambda 2 are negative numbers, and therefore the y converges to 0. That's case 1. Case 2, lambda 1 equals lambda 2, repeated real root. Mathematically, repeated real root, and physically, that's called critical damping. And this is going to look, these solutions look like this. E to the minus lambda t, lambda will definitely be negative for this thing turns into 0. So it's minus c over 2m. So it's a negative number times, and then you're going to have some sinusoid in here. Nope, wrong. Sorry. That's the next case. If this is 0, repeated real root, you're going to have at plus b, a linear function times the exponential. Let me just put those pieces together so they kind of look like they belong together. Well, this also converges to 0, and you can prove that it crosses the t-axis at most once. That's critical damping. And the last possible case is underdamping. That's going to be two complex conjugate roots. And I might write it this way, minus alpha. For the same reason that we argued up here, it's minus c over 2m. That real part is always negative.
The at plus b is the same as c1t plus c2?
Mm-hmm. Yep. Oh, I should repeat for people online. The question was this, at plus b, does that mean the same as when you wrote c1t plus c2? Yes, it does. They're just arbitrary constants. So in this case, y is going to be e to the minus alpha t, and then you've got a cosine omega t plus b sine omega t. And this is when you get these solutions where you have a declining, decreasing exponential envelope, and then a sinusoid fits inside of there. So it's a sinusoidal signal, but it's being exponentially attenuated. So underdamping, overdamping, critical damping. If you draw the curves, the overdamping and the critical damping to the human eye look pretty much the same. You don't really see much difference. This one can cross the t-axis at most once, For instance, if the A were positive and the B were negative, then there will be a point of intersection. But what we mean by that is you're getting a response that looks like this. Or, you know, it could be flipped over the other way. But it crosses the t-axis once, not twice. This is an asymptote here. Here, it might never cross at all. Of course, it might never cross here as well. But you might get a solution that looks like this. So it's like you lift the mass up a little bit and you let it go. It's got so much damping, it just settles back towards the equilibrium position. Doesn't cross it and then come back. So both of these cases, they either cross the t-axis never or once. They cannot cross twice. This one, under damping, is oscillatory. It definitely will cross the equilibrium position infinitely many times. But the signal is degrading pretty quickly. So, you know, that's infinitely many times, that's mathematical theory. In real world systems, what you see is eventually the thing just stops. If it's moving, it's moving such a tiny amount, you can't perceive it. For engineering purposes, if you can't perceive the movement, it's not there, right? Jeffrey?
It's not possible to have two distinct, like any of the positives for overdamping.
Oh, you mean like this could not cross the t-axis twice?
I mean, like for overdamping.
No.
One and two can't be above 0.
It could possibly cross once,
This once.
but not twice. And you can see that mathematically. We're thinking of this. If you had your linear combination, you have some constant times e to the something t. And it's going to be a negative number. This could be negative or positive. We don't have any control over the cafe. Likewise, this could be negative or positive. And you'd have e to some other negative number, let's call it minus ct. Now, set that equal to 0 and see if you can solve it. Well, there are some cases where you could get a solution, I think. Let me see if we could get it. First of all, I could divide, say, by e to the minus ct. So I'd have a e to the minus k plus c t plus b equals 0. Now, if I put this on the other side and divide through by a, okay, now, if this number turns out to be like a positive 0.6, and this number here, c minus k, is negative, these are both ifs, if, then you could take the log of both sides and you could solve this equation. But you'd get one solution, right? Not two, you'd get exactly one. On the other hand, there's times when it would have no solution at all. What if A and B have the same sign? Say they're both positive. Then, did I do this right? Shoot. When I push that B over there, it becomes negative. So if A and B are both positive, this is a negative ratio. And there's no way you're going to get a negative ratio out of e to the something t. So it might not have a solution, but if it does have one, it will be only one. Which is to say that that curve could cross the t-axis once. It may not cross it twice. It may not cross it at all. And by the way, this falls into your ordinary experience. You go to most modern cars, and gently now, you don't want to put a dent in it. Put your hands on the, or in the hood area, up over the headlight where it's fairly well braced, and just push it down and let up. what you don't see is the car starts going boing, 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 boing. No. As a matter of fact, what it probably does is it only goes down a tiny little bit and then it just comes back and stops. So that means you're getting this kind of a solution. I'll invert the negative so it looks right. At the initial point, it's pushed down and then it just settles back up to the upper position. But, you know, if it's in a pickup and Bubba and his 6 buddies are out drinking, when they jump out or when they jump in or when they throw in the keg of beer, whatever happens, you could possibly see this kind of behavior. The initial displacement or the initial velocity is large enough to get it to cross the equilibrium position once. It won't do it twice, unless the shock absorbers are shot, in which case you're in underdamping. And now it does go boing, boing, boing. Whatever that means technically. By the way, for people online, I am watching the chat box here. So if anybody has a question, you're free to type it in there as well.
Could you go over variation of parameters?
Oh, variation of parameters? Oh, I can talk through it quickly. It is, if I just make up a problem, I'll probably get some crazy mess I can't evaluate, but I could get started. First of all, variation of parameters applies to a second order linear differential equation, a single one. Oops, I need a y here. These coefficients, the p, the q, and the r, have to be continuous on the interval where we're trying to solve the equation. And it has to be that somehow you can come up with 2 solutions, y1 and y2, that solve the homogeneous equation. Homogeneous equations when you set r equal to 0. Now, if you have such an equation and you've got 2 linearly independent solutions, then you can compute the Wronskian. Like so, and this is guaranteed to be a particular solution. In other words, this is a solution that when plugged in here will generate the right-hand side. And it's minus y1 integral y2r over w dx plus y2 integral, let's see, y1r over w dx. Okay, well, that's all well and good, but how about an example? That's probably what you wanted to see, or did you have a particular one in mind, Jack?
I didn't have a particular one in mind.
Okay, I'll cook something up, which I hope I can finish, but I'm not promising. So let's take something that's actually not too awful. How about y double prime minus y prime plus 6y equals, now the reason I'm choosing this is for the homogeneous equation, I'd have the characteristic equation be lambda squared minus lambda plus 6, I probably don't want that, minus 6. Set that equal to 0. That would factor to lambda minus 3, lambda plus 2. So my y1 and y2 are e to the 3t, e to the minus 2t. Okay, now let's just think of some kind of a right-hand side. Honestly, they're all, anything I could put in here is going to be really unpleasant once you get to the integrals. But how about this? Why don't I pick a YP, x plus 1, and see what happens when I run it through here? Well, y double prime is going to be 0. Minus y prime is minus 1. Minus 6y is minus 6x minus 6. So that would give me minus 6x minus 7. So if I want, I can find my two solutions to the homogeneous equation pretty quickly this way. And I can compute the Vronsky pretty well. E to the 3t, e to the minus 2t. Now take the derivatives. 3e to the 3t and minus 2e to the minus 2t. Vronsky, this times this is minus 2 e to the t. This times this, when I'm subtracting, I'll have minus 3 e to the, well, e to the 3t times e to the minus 2t is e to the 3 minus 2, or e to the t. Plus t. Plus 3 minus 2. So the Vronsky is minus 5 e to the minus 3t. So variation of parameters formula tells me this. A particular solution, we're trying to get to this guy up here, the x plus 1, is minus y1 integral y2r over w dx plus y2 integral y1r over w dx. And now we'll plug this in. Minus y1 is minus e to the 3t. y2 is e to the minus 2t. R is minus 6x minus 7 over w. W is minus 5 e to the t dx. So that's this part, plus y2. Y2 is e to the minus 2t. Then e to the 1, or e1 is e to the 3t. R is that mess over w. Oh, now I've got t's and x's all mixed up here. Let's make them all x's. Well, here's the simple fix. Where t equals x, okay? So take your pick. All t's are all x's. Now, this is frightful, right? You've got an exponential times a linear function in every case, so you're going to have to use integration by parts, and these are awful fractions. And if everything's set up right and you do everything perfectly at the end, all of the nasty stuff will cancel out and you'll get something like this. Now, it takes a lot of work to set up one of these so that it comes out nice. Well, actually, there's two ways. You do a lot of work, kind of gain some insight, guess and check, and eventually you get one that's doable on an exam. Or number two, you pick it out of a textbook where somebody else has already done that for you. Or you make it trivial. You know, make the right-hand side 6. Well, then these become very easy to do.
So can you explain when we use this?
Yes. When you have, first of all, the first thing we did was something like this. Constant coefficients, right-hand side of 0, and then, you know, you have the 3 cases for the solution of the characteristic equation, and you're just done. Now, the next step up for constant coefficient equations was you might have something like, well, minus 6x minus 7 is not so bad. You might have something like this. So then you ask yourself the question, could I guess the form of the solution? And in this case, the answer is yes. If I'm going to generate a first degree polynomial, and all I get to do is take linear combinations of the function, its first and its second derivative, then I must be starting with a first degree polynomial. So I take its form, take 1 and 2 derivatives, plug it in here, solve it, and I figure out what y is. By the way, variation of parameters is not the way to do this. You would do it in the way I'm describing here. This is called undetermined coefficients. Now, what if though the right-hand side, and you know, it might as well be this one that we had in mind here. What if the right-hand side is something where you can't just guess what this looks like? And this happens all the time in real life. Sine x over x, for instance. Well, I don't know what form would generate this. The ones we can guess is if you have polynomials, exponentials, sine and or cosine, or exponentials times any of those things I said earlier. Well, this doesn't fall into that category. So in this case, if you can do it by formula, you would do it by variation of parameters. But honestly, the variation of parameters formula is so complicated, it's the method of last resort. Generally speaking, you don't want to go there if you can avoid it. Does that help any?
Yeah, that helps. Thank you.
Okay. And all of the textbook examples, they're carefully picked up so that these integrals are at least doable. But even then, a good many of them involve the parts formula. And sometimes, some of them, I remember working some, you got to do parts 2 or 3 times, and oh my gosh, it's awful. Now, nowadays, what I do when I run into that is I open up my web browser and I type in integral calculator. I pick one of those sites, I type in my integral, and poof, it pops up and I write it down. Not so good for an exam, but then again, that kind of question wouldn't be so good for an exam question, right? My general advice about that sort of a mess, if it does come up on an exam, when you get to that point, at that point, you've got the problem set up, right? So surely you've got partial credit. If I came along, if I were doing integration by parts, I ended up with something like this, x squared plus 3x minus 1 cosine of 5x dx is in my problem somewhere. At that point, I would move on. I would. Now, I might come back later, but my strategy when I'm taking an exam is to convert minutes into points. And this is going to have a low yield. So I'm not doing it until I don't have anything else I can gather points from. So I have a simple strategy on that sort of stuff. And it worked, you know, I graduated. So give it a try. And the other thing is sometimes if you generate an integral, it's just a nightmare in the middle of the exam. It's oftentimes because you made some simple mistake ahead of time. So even if you work it out, it's not going to help. once you got to that point, the grader's going to read it and say, oh, they knew the formula, they knew how to set it up, but they made a mistake. I see they dropped a minus sign. Well, your points collecting is over, whether you evaluate that messy integral or not, right? So. Tommaso.
Yeah, about the integrating factor itself, it said that there are not very many rememberable equations for them, and they will be provided as an email. We'll get the integrating factor.
Yeah, there's a couple of formulas for integrating factors, and I don't know about you, I cannot keep those things in memory. So I either have to derive them or look them up. And my thought is, look, if I can't remember, the students probably can't either. So I promise you, actually, I can show you the formulas will be provided. I think I might have it here, is what I'm looking for. Yeah, so I'll show you the first page of the exam. How's that? Just for showing up tonight. It doesn't help that much. See this? The formulas I promised to provide are below. You may or may not need them. So I'm providing a little help, but not too much. But if you need them, there they are, okay? And if they're wrong, that's my fault, not yours.
If we're doing stuff with n by n matrices on the exam, can we expect some nice 2x2s, or are you going to have some 3x3s in there?
Okay, the question is, what about matrix problems? I'm paraphrasing here. None of my students are quite this impolite, but some of these things are an absolute horror. And if you give us one of those, I'm not going to be happy. I will not give you a horrible matrix. However, I am assuming that you have like this kind of a calculator, a TI-84 or better. And so you could do things like row reduce a matrix fairly quickly if you needed to. Now, would I give you a 5x5 matrix? No, there's no reason to do that. I can learn anything I need to know about what's in your head by stopping at a 3x3. So certainly not more than a 3x3. And if it is a 3x3, it's probably going to be a nice one.
Like when there's 2 zeros on the top line?
For instance, yeah. Yeah, if I just take a random 3x3 matrix or you write one down and you hand me the paper and say, okay, smart guy, find the eigenvalues, I'm going to be at it for a while. You know, I'm probably, and I might not ever get them exactly. So it's probably going to be a nice one. But you should remember that there are a couple of things about these matrices. If it's symmetric, in other words, if the transpose of the matrix equals itself, if it's skew symmetric, so the transpose of the matrix is equal to the negative of the matrix, or if it has n distinct eigenvalues, not vectors, eigenvalues. So if it was a 3x3 and the eigenvalues are 1, 2, and 3, it's got 3 different eigenvalues for a 3-dimensional matrix, then it's absolutely guaranteed to have 3 linearly independent eigenvectors. And so you will not be in some horrible, messy case for writing down the solution to an ODE. And furthermore, by doing things like packing zeros in the right spot, I can make the eigenvalues easy to compute if you know what you're doing. So for instance, if there's some row or column that has 2 out of 3 entries are a 0, you can subtract lambda down the diagonal and compute the determinant pretty quickly with high school algebra. I really do try not to give problems that produce these rat's nests of calculation on an exam. I don't think it's helpful. And if you come across one, then it probably means one of 2 things. Number one, I made a mistake, in which case you're not going to get it solved anyway. It's a horror. So you write down enough to indicate that you know what to do and move on. Or number 2, you made a mistake, in which case you still do the same thing. You write down, I can't seem to get this to work out. Here's the general method. And I read it and I think, oh, well, he or she knew generally what to do, just couldn't make the calculations work, and you get your partial credit. Okay.
Sounds good.
Any others? Do you, it ended, I'm so sorry to say, but there used to be a wonderful program on National Public Radio called Car Talk. I don't know if you heard it. Problem is, one of the guys who did it died, and that made it really hard to continue with the program. But they gave advice on fixing cars, and they also did a string of essentially stand-up comedy the whole time. It was really funny, and they actually knew what they were talking about mechanically, so I like that. But they always ended with this phrase, except they had 1 hour for their show, so I'll modify it slightly. The time has come. You have wasted 2 perfectly good hours yet again on a lecture in differential equations. Just think, it's all in a book somewhere. You didn't have to pay for it. You could have just read it.
I haven't had the best luck with reading math books.
It is a real skill. I will. Oh, that's true. You can't get credits for it. You know, by the way, class is over. Feel free to leave. It's one thing I really do think the internet has started to do for us, though, is begin to democratize education. You can, like some of these MOOCs that come out of these high-class schools, some of them are really good. Like, I mean, why would you listen to me when you can get MIT's courses on linear algebra and differential equations for free? You can. Gilbert Strange, he's famous. No one's ever heard of me.
I watched a few of his videos. They're quite good.
What's that?
I watched a few of his videos. They're quite good.
They are good. He's an excellent teacher. And he's a brilliant mathematician. His course is way better than this. Go take it.
Are there solutions to the homework sets, the 7 and 8?
I'm working on them right now, okay? But I plan to post them
All right.
as quickly as possible.